All right, so what I was saying is that for trigonometric integrals, there's certain rules that applies, all right? So I'll go through it again very quickly. We say that the power of cos is odd. And when we say odd, remember when we say odd, we say n is equal to 2k plus 1. All right, that's the definition of an odd power, all right, where k is an integer. So, for example, you're going to get powers like 3, 5, 7, and so on, all right? So if the power is odd, we say you save one cos, then you use the identity for cos squared to convert the remaining factors of cos in terms of sign. Then your substitution, there's just going to be u equals to sine x, all right? Now, if the power of sine is odd, you save one sign, and then again, you use the same identity to convert the remaining factors of sine in terms of cos, and your substitution is u equals to cos, all right? Now, if both of them are even, so if both powers of cos and sine are even, we say we use the half angle identities, and I've already explained how we get to this half angle identities, all right? It comes from what cos 2x is. We say cos 2x is 2 cos squared minus 1. If you make cos squared the subject, there we go, you have your half angle identity. And again, cos 2x can be written as 1 minus 2 sine squared. If you make sine squared the subject, then you have the other half angle identity, all right? Now let's look at the example. Example 1, we have to integrate cos cube. If you notice it, there's only cos, there's no sine. There's only one function there, which is cos cube, all right? You apply the same rule. The power of cos is odd. What does that mean? Because the power of cos is odd, remember there's a 3 there, the first rule says you're going to keep 1 cos x, all right? There we go. That's the first step. The second step says use the identity to convert the remaining factors of cos in terms of sine. There we go. Cos squared is 1 minus sine squared. You see, I'm going step by step. And now I can do a u substitution. Your u has to be sine. Why? Because if I differentiate sine, I have cos. And cos actually appear in the integral. There we go, there's cos there. All right. You want to make your u to be sine, because if you differentiate that, it will cancel with this cos here. Now, if you do that, then you just need to substitute. And obviously, after integrating, make sure you add plus c, very important, all right? So change the u back in terms of the substitution you make, and then add plus c. Why? Because it's an indefinite integral. Let's look at another example. Now you have sine to the power 5x cos to the power 2x, all right? Sine to the 5 cos squared. I'll go through it again. Notice it, sine has an odd power, all right? What does the rule say? You keep one sine, that's the first step, keep one sine. The next step is convert the remaining factors of sine using the identity to something that looks like cos. So sine to the power 4 is the same as sine squared all squared, all right? And sine squared, we know is 1 minus cos squared. Since it's the power 4, we need to take all of this squared. And what is the substitution? The substitution is just u equals to cos x. Remember, if you differentiate cos x, you have minus sine x. Very important, there's a minus sine x, all right? And there you go. After doing this substitution, it becomes straightforward and easy. Let's see what happens. It just becomes an easy substitution, expand, integrate, substitute back the original function, and then add plus c. Straightforward. Now, for example, 3, if you notice it there, they're using half angle identity. We've already discussed that. So this one also should be easy. So for example C, for example 3, sine squared, we said is half into 1 minus cos 2x. Please don't memorize stuff. Some of you memorize stuff and you end up having a plus there instead of a minus. Where is that coming from? This is how you're going to do it. Ask yourself, where do I get the half angle identity for sine squared? Write it out. Cos 2x is 1 minus 2 sine squared. Therefore, if I make sine squared the subject, I get half into 1 minus cos 2x. There you go. That's how I got this value here. So if you've forgotten it, just start from here. Do this all over again. Obviously, if you integrate this, so what I wrote here is just for illustration sake, if you integrate cos of ax dx, careful, it has to be 1 over this coefficient of x. So 1 over the coefficient of x is a, so 1 over a. The integral of course is sine, so you have sine of ax. Similarly, if it was sine ax, you could have had minus 1 over a cos ax, all right? Even when it comes to e to the power ax, whenever you integrate in a function with some coefficient, you start by taking 1 over the coefficient. Very, very important, all right? So using that same idea, if you integrate this piece here, notice it, you just get 1 over the coefficient, which is 2, and then integral, of course, is sine. Then you need to apply fundamental 12 calculus by 2. So you're going to substitute this upper bound, then you're going to subtract it with the substitution of the lower bound. All right. Straightforward and easy. Any questions so far before I continue? Guys, ask your questions. Any questions? All right, no question. Example 4 looks like what I did earlier. So if you have sine to the power 4, again, it's an even power. Even power, first thing that comes to mind is have angle identities. But look at what happens this time. You have sine squared all squared, all right? So you have sine squared all squared. The half angle for sine squared is half into 1 minus cos 2x. This is square outside, means I need to square everything. So if you square everything out, you get this whole piece here, all right? Now you need to integrate each of those. We know how to integrate 1. We know how to integrate cos 2x. The problem is this, you have cos squared of 2x. You can't directly integrate it. Most of you make the mistake, you want to directly integrate it. Because it's a squared here, we need to still apply half angle identities again, all right? So let me scroll down so that you see what it looks like. So notice it, I'm going to explain step by step. If you have cos squared of x, remember that you get half into 1 plus cos 2x. Now you have cos squared of 2x. What has changed? You've doubled this angle here. You started from x, now you have 2x. All you need to do is you go back to this half angle that you know, where you see 2x, just double that as well. So you get 4x. Please keep that in mind, all right? So it means that if I give you cos squared of, let's say 3x, what are you going to do? You go to this original half angle identity where you see 2x, you multiply by 3, so you get 6x, all right? So in the place of cos squared 2x, we're going to replace it with half into 1 plus cos 4x. Why do I now have 4x? Because I doubled the angle there. Therefore, I need to double this piece here as well. All right. And obviously, after doing that, everything becomes straightforward and easy. It just becomes something that everyone can do. Please always add plus c. Very, very important. For an indefinite integral, make sure you add plus c. And notice it, you have 1 over 4 because I told you if you have a coefficient, you need to take 1 over the coefficient before integrating the function itself. All right. Now I'm going to explain this. So technique for integrating tan and sec. This is how it works. So if you have a combination of tan and sec, the first thing you look at is the sec. So sec is the most important there. If the power of sec is even, then you need to save a factor of 6 squared. All right. Remember for sine, of course, we just keep in 1 factor, right? Not the square. But for sec, you keep in a 6 squared. And then obviously you're going to use this identity 6 squared equals to 1 plus tan squared. The idea is to try and convert the remaining factors of sec in terms of tan. And then your substitution is u equals to tan x. Why? Because if I differentiate tan x, what do I get? I get 6 squared. You see why you kept the 6 squared in the first place. because if you differentiate this u, you get that factor that you kept, all right? Similarly, if you have tan x this time is odd, then you have to save, look at this carefully, sec x and tan x. And you use this identity to convert the remaining factors of tan in terms of sec. Your use substitution is sec, very important because if you differentiate sec, you have sec x tan x. So the first thing you do is you check the power of sec. If it's even, all right, I have to stress a little bit more on this power. So this power there is n equals to 2k, all right, where k is an integer. If you check in the textbook, they specify that k needs to be strictly greater than or equal to 2. All right, so it means you're going to get stuff like 4, you're going to get stuff like 6, and so on. All right. Now let's look at this first example. If you notice it in this first example, the power of sec there is even. All right. So we don't care about the power of tan anymore. So the first you look at is the power of sec. If it's even, the first will apply. If it is odd, then you go ahead and look at the power of tan. All right. So it doesn't matter what the power of tan is. The focus there is the power of sec first. So because it's even, we apply the rule. We say we keep 1 sec squared. And then this remaining sec squared, you see we convert it to the identity. So 1 plus tan squared. And there you go, you're ready to use your u substitution, which is u equals to tan. Then it makes life very easy. So if you apply the theory or the concept nicely, notice that you're going to get a very quick and easy answer. But if you use the wrong substitution, then it's going to get even way complicated, all right? All right, after doing the substitution, notice it becomes straightforward and easy. You just integrate u to the power 6 plus u to the power 8. And obviously convert the u back to the original function, which is tan x, and then you add plus c. Straightforward and easy. Let's see if there's any other quick example we can do. Example 6. Now look at example 6. This is a situation where the power of, so you start with sec as usual. We see that sec is odd, therefore we can apply rule number 1. So we check the power of tan now. It's odd. There we go, we can apply rule number 2. What does the rule say? It says that you're going to keep a factor of sec x or sec theta times tan theta, since we're dealing with theta in this case. So sec theta times tan theta. Now you need to convert the remaining factors of tan to sec using the identity, all right? We know that tan to the power 4 is just tan squared all squared. All right, take note of that. So tan squared all squared is the same as tan to the power 4. So what is tan squared? It's 6 squared minus 1. Once you reach this step, you're good to go. You can already let your u to be sec theta. Why? Because the derivative of sec theta is just sec theta times tan theta. And then it becomes a very easy integral. All right. There we go. You let u to be sec. You just get sec theta, tan theta, d theta. You substitute and simplify. Straightforward and easy. Everyone can do that. You just add the plus c. All right. What you see there in the box is something that you need to know. You don't need to prove. All right. This example means that, so if I say you need to know the following, means that you just need to state this kind of integral. If you see integral of tan, just tell me that it's equals to ln absolute value sec x plus c. Don't go ahead and try and show me the u substitution, how you got to the result, all right? I don't care about that. And then integral of sec, just tell me that it's ln absolute value sec x plus tan x. You get your full marks, all right? You don't need to prove how you got there, all right? But everything x, obviously, you need to prove how you got there, except this 2, which I put in the box. Now let's look at the integral of tan cube. Integral of tan cube, again, you notice that there's no sec, so it means that rule number 1 is gone. We're looking at rule number 2. The power of tan is odd. Now that the power of tan is odd, remember in this case, you can save a factor of sec and tan because there's no sec here in the first place. So the first thing that comes to mind is tan cube is just a tan squared times a tan. All right. Now looking at this, what do you do with this? The next thing that comes to mind is identity. So I'm going to tell you a very quick hint. Whenever I give you an integral and you try to simplify, you don't know what to do, think about identity. If you see most of the questions that we've done already, the identities helps a lot. Once you start applying the identity, you're going to see how the solution is going to come about, all right? So in this case, if you see tan squared and a tan, the next thing that comes to mind is, what is the identity there? Tan squared is 6 squared minus 1. Therefore, if I apply that, let's see what happens. Just gonna scroll down quickly. Notice it, 6 squared minus 1. If you multiply out, now you have two functions. You have 6 squared tan x minus tan x. We already know the integral of tan x. Do we know how to integrate 6 squared tan x? Yes, it's just a u substitution. If you let u to be tan, the derivative of that is 6 squared, therefore it's just a u substitution. You see, just by playing around with your identities, it becomes something that you can easily solve. All right. You see there, I'm just showing you how we did the integral of 6 squared tan x. Just let u to be tan. Derivative is 6 squared. You just end up integrating u to u, which is u squared over 2. You just end up with tan squared x over 2 plus c. Therefore, that integral is tan squared x over 2 minus ln absolute value 6x plus c. All right, straightforward and easy. Example 8 is sec cube. All right, the power of sec this time is odd. Like the previous example, just write this as sec times a sec squared. And the answer says, what can I do with a sec squared? You think of an identity. We know that there's an identity that says 1 plus tan squared is 6 squared. So in the place of 6 squared, you can use that identity. But be careful. Before I explain why we're using by part, you're going to notice that it's going to run in a loop. So if I ask you an integration problem, and then you end up going in a cycle forever and ever, you know that you're using the wrong method. So your quick guess here is integration by part. Let's see why we're doing integration by part. I can easily integrate 6 squared, and I can easily differentiate sec. All right, that's why we choose integration by part. All right. And if you do that, look at what happens. You end up with sec x tan x minus integral of sec x tan squared x dx. There you end up with a tan square, which again, you can use the identity, which is 6 squared minus 1. If you multiply out, look at what happens. You have a sec cube that appears on the right-hand side, and there is another sec cube on the left-hand side. What do we do with integrals that are the same? You group them together. So you take the minus sec cube to the other side. You just have 2 of them. There you go, you're done. You divide all 2 by 2, and you're done. All right.